As I've shown earlier, when you use the FTCS scheme, we may encounter some kind of instability with the numerical algorithm. So one way to check whether the scheme that we come up with is stable or not is to use the von Neumann stability analysis. In the handwritten lecture notes, I've mentioned some of the assumptions that we do in order for us to use the von Neumann stability analysis. So I would advise you to download those handwritten notes and go through them before you proceed on with this part of the lecture. So with the von Neumann stability analysis, we assume that the delta t and the delta x that we use are very, very small. So assuming that we are only concerned about a very, very small period, the solution that we get, or the solution of the one-dimensional heat equation, can be approximated by the first term or the sole term in your Fourier series, which can be written as a to the power n of eikj delta x. So a here is an amplitude factor which can in a way governs the error of your numerical solution. E is your typical exponential, I is an imaginary number, k is the wave number, j basically represents the j index that you see here, and delta x is your step size. So for us to do the von Neumann stability analysis, what we want to do is we want to substitute this entire expression here into the place where u appears in your numerical scheme, in this case the FTCS scheme. So when we substitute this approximation into u, on the left hand side you have uj at n plus 1. The approximation that we had was uj at n. So what we do to do this substitution is, if it is n plus 1, we are just going to write it as a to the power of n plus 1 of eikj delta x. That is on the left hand side. On the right hand side, we are going to do the same thing. So this is j, but here you have j plus 1. So what we do is we are just going to replace the j with j plus 1 delta x. So the rest would follow suit. Now, once we have made the substitution, what we are going to do next is we're going to divide both sides by the same expression that we just substituted in. Remember, the whole point of this von Neumann stability analysis is to look at what the expression for A is. Okay, so if we divide both sides by this expression, this is going to end up being A, because A to the power of n plus 1 divided by A to the power of n is just your A, where the exponential term will cancel off. So on the right hand side, you have the coefficient multiplied by exponential terms of eik delta x minus 2 plus e minus ik delta x. Okay, now having reached here, what we are going to do next is we are going to use the Euler formula to further simplify the exponential term that we have. So the Euler formula that we are going to use is actually given by cosine k delta x is essentially half of eik delta x plus e negative ik delta x. So what we're going to do is we're going to substitute these two exponential with the cosine of k delta x. So when we do that, the expression for A becomes this. Okay, so if I move the 2 out from the brackets, then this will be 1 and my 2 will come over here. So now I'm going to use the double angle formula to further convert the cosine k delta x. So from the double angle formula, we know that the cosine of k delta x can be written as the 2 cosine square of k delta x over 2 minus 1. So this actually comes from your cosine 2 theta is equals to 2 cosine square theta minus 1. Okay, now if I make use of the this trigo identity of sine square theta plus cosine square theta is equals to 1, I can further simplify this to 1 minus 2 sine square k delta x over 2. Okay, so if I replace this entire expression back into my cosine k delta x, the expression for A becomes, after some mathematical rearrangement, we get 1 plus 2 alpha delta t over delta x squared of sine square k delta x over 2. Sorry, this should be a minus and this should be a 4. So I'll get this after substituting cosine k delta x with this expression here and doing some mathematical rearrangement. So this right here is the expression for A. Now, why do we need to find the expression of A? If you recall from the von Neumann stability analysis, you have Ujn to be given by An Eikj delta x. So this A, like I mentioned earlier, is an amplitude or an amplification factor that would amplify your error if this A is not controlled. Okay, so if you look at this expression here, the error for your solution U will be decreased if the simulation or time step increases if the magnitude of A is less than 1. Because if the magnitude of A is less than 1, anything that is less than 1, when you raise the power, it is going to decrease. Okay, so if A is less than 1, we know that A will approach 0 as n increases. So in other words, the error in your solution will decrease if the number of steps, time steps increases. However, if A is greater than 1, the opposite will happen. Now, how do we know if this magnitude of A is greater than 1 or less than 1? So we want this condition over here. So in other words, we have 1 minus this of sine square k delta x over 2, and this must be less than 1. And if I open up the modulus, then I will have negative 1 to be smaller than the term for it. So let me rewrite this again. Alright, now to further simplify the thing, let's say I move the 1 to both ends here. So if I move the 1, this will become 0 and this will become minus 2. Okay, and we'll get rid of this 1 in the middle. Now, the way to analyze this is to look at two of the limits. So the first limit would be this limit over here. And if you look at this limit, you can see that the value of sine square is going to be positive because of the square term. Delta t is positive, delta x is also positive. Alpha is the thermal diffusivity, which is a material property, and it is also positive. So if everything here is positive and you multiply with a negative sign, it is always going to be less than 0. So we already satisfied the first part. The second part is actually this part over here. Okay, now if you look at this part, I can rearrange this to give 4 alpha delta t of sine square k delta x over 2, and this must be less than 2. Okay, now if I move the 4 over, I'll get alpha delta t over delta x square must be less than 1 over 2. Now, when you look at this, the value of sine square is between 0 and 1. Okay, now if we want this entire expression to be less than half, it means that we have to consider the largest value of sine so that we can test for the strictest criteria possible. So considering that the largest value is equals to 1, what we get eventually is we get alpha delta t over delta x square must be less than half. Okay, so what is delta t? Delta t must be less than 1 over 2 alpha times delta x square. And this right here is known as the stability criteria for the FTCS scheme. So what does this stability criteria means? It means that when you actually solve the heat equation using FTCS scheme, your delta t and delta x must be selected such that the delta t is less than delta x squared divided by 2 alpha. Okay, so if alpha is equals to 1, then your delta t must be less than half of delta x. So if delta x squared. So if your delta x is let's say 0.1, then your delta t must be less than 0.005. And this can be problematic because if you have to do your discretization in x such that this delta x here is very, very small, let's say 0.001. Okay, and you're solving from x equals to 0 to x equals to 1 in the x direction, and in the t direction you're solving from t equals to 0 to t equals to 100. Now if delta x is 0.001, assuming that alpha equals to 1, then delta t must be less than half of 0.001 squared. Okay, so this would be around 3 6, so it will be 0.5 times 10 power minus 6, which is approximately 0.5 microseconds. So for you to solve from t equals to 0 to t equals to 100, your delta t must be less than 0.5 microseconds. This becomes problematic because to march from t equals to 0 to t equals to 100 at a time step of 0.5 microseconds is going to take a long time to reach. So this is why there's a huge restriction to how we can solve the heat equation when we use the FTCS scheme.